guys, this is the first in a possibly infinite series of me explaining quantum mechanics concepts until I'm satisfied with how I've explained them. So we'll be starting from the bottom, which is funny because an infinite potential well is infinitely deep. But yeah. We're starting from the bottom. This is like the essential concept that shows you why quantum mechanics is called quantum mechanics and everything like that. Yep. Okay. So, what is an infinite potential well? Well, this is like our x-axis. Let's say that this is 0 and this is A. We want the particle to be trapped in a well that's infinitely deep. So this is how we draw it. This thing right here is the well, this part of the x-axis, and the rest is infinitely high, okay? So this is a potential of V equals infinity, V equals infinity, and over here we have V equals 0. Why does this potential matter? Well, if you'll recall, the Schrodinger equation has a potential term in it. We've got, let's write it like this. We've got p squared over 2m psi of x double prime plus v of x psi of x equals e of x. This is the Schrodinger equation for a time-independent particle. Well, the time-independent version of the Schrodinger equation for a particle, and as you know, or you might not, this wave function psi of x, oh, pardon me, this isn't right, e times psi of x. This wave equation is the square of its amplitude is representative of the probability that you'll find the particle in that location. So if you were to integrate from way over from the left of the x-axis to the right of the x-axis of the square of the amplitude or the modulus of the wave function, you would have to get 1. Rather, the probability that you'll find the particle somewhere in the x-axis is 1. Now, that's in the regular case, I mean in the general case, but in this case, we actually have that the integral from 0 to a of psi of x squared dx is equal to 1, because the particle cannot be anywhere over here or over here. It can only be over here. Why? Well, I mean, for logical reasons, it can't be where there's an infinite potential, because there's no way for it to get over. But for purely mathematical reasons, when v of x, when the potential blows up to infinity, this guy, right? We have something plus infinity times something else equals yet another thing, right? Well, for all of this to be balanced out, we notice that we have psi's everywhere. So there's a psi double prime here, a psi here, a psi here, and then whatever. Well, the only way to balance this out mathematically would be that psi goes to 0 everywhere, except when v isn't equal to, when v isn't equal to infinity. So we have that if v is not equal to 0, then psi is equal to 0. So that's what we're looking for. And that's why we limit ourselves to this integral, because we can split minus infinity to infinity to minus infinity to 0 plus 0 to a plus a to infinity. And then this integral is 0 and this integral is 0 because psi is equal to 0 for this guy and for this guy. Okay, so now that we have all of that handled, we can go ahead and put in our 2-point boundary values. So we want psi of 0 to equal 0. And we want psi of a to equal 0, right? So we've got psi of 0, 0, psi of a 0, and that balances out the infinities. Okay. And now we can start solving. What makes it really easy is that the v of x term is 0 for the interval 0 to a. So this is the interval we're solving on. And on that interval, v of x is 0. V of x is 0. So that's pretty nice. Now all that we're left with is p squared over 2m psi double prime is equal to e psi. Now, what I haven't mentioned is that the p, which is momentum, right? It's defined as, well, in quantum mechanics, it's defined as minus I h bar. Oh, pardon me. Yeah, it shouldn't be. Well, that's pretty crappy. Minus I h bar d by dx. So that's where the derivative is gonna come from. It's pretty much the shittiest thing I've written so far, but yeah, you'll excuse me. There will be another version anyways. So if it's defined like that, then when we put this guy into here, we will get h bar squared over 2m with a minus in front, and psi prime is equal to e psi. Now we can go ahead and divide the whole thing with 2m, rather multiply with 2m over h bar squared. We can put in a minus as well, and we can call 2me, these are all constants. I mean, obviously mass and energy are gonna depend on stuff, but they don't depend on x, is what I mean. We can call that k squared. And so if we put this on the other side, we are gonna have psi second, or psi double prime, however you prefer, plus k squared psi equals 0. Okay, so let's call this 2 and call this 1. So with 1 and 2, this is how we solve our differential equation. We have the conditions, we have the equation, right? In general terms, you know that psi of x is a sine kx plus b cos kx. Now, I could derive this for you, or I could just show you by plugging in, although that wouldn't really prove that it's orthogonal. But, so if you just think about it, if you put in sine over here, if you put in sine over here, you would get minus k squared sine kx. Put in cos, you would get the same thing with cos, so that's why the plus cancels out. Now this superposition of sine and cos is the most general solution, so that's why that's the solution. And now we just plug in. We get that psi of 0 is supposed to be equal 0, and that is equal to b. So we get that b is equal to 0. And then psi of a is also supposed to be equal to 0, but that's equal to a sine ka, right? Well, if we set a equals to 0, and then we don't have 0 to a, psi squared dx equals to 1. right? So we wouldn't have that. So we cannot have this. We cannot have a equals to 0, which means that sine of Ka is equal to 0. But as we all know, that doesn't mean that Ka has to be equal to 0. Nope, it actually means that Ka has to be a multiple of pi. We set n to be from natural numbers. There's a reason for setting it from natural numbers and not whole numbers. The reason I believe, well, yeah, the reason is that it doesn't really matter because we only need k squared. K squared is what we can observe, not k. That should be the reason. So we got k squared equals n squared pi squared over a squared. That's the one that matters. And so if we had n from whole numbers, right, n from z, then that would just be repetitive, twice repetitive. But it just can't happen. We're gonna have repetitive energies later, but not here, not here. Because why are we interested in k squared? Because k squared is 2me over h bar squared. That's equal to n squared pi squared over a, right? So from here, we get that e, and I'll just put a little sub n, because it clearly depends on n. E sub n is equal to, now it's usually written like this, p squared h bar squared n squared over 2ma squared. So you've got, let's look at what the energy depends on. So if you notice, we were given the energy, or I mean, we weren't really given it, but we had the energy in the equation. But now we say that there's only a solution to this equation if the energy satisfies some equality. And what is that equality? Well, first of all, we got the mass, right? We've got mass. What's interesting is that we've got the width of the well in the expression. So if it were infinitely thin, the width, right? Then you would have huge energy steps, right? You'd be dividing by 0, which would mean that you've got something infinite, so the steps would be huge. Now, as the well's width increases, so do the energy steps decrease, and you end up not having discrete energy. So let's think about that for just a second. Let's think about the limit as n approaches infinity. Pardon, as a approaches infinity of En. Well, that would be, you'd be dividing by something infinite squared, right? So, well, okay, yeah, you can see it like it's just the limit of a goes to infinity of 1 over a squared, which is 0, right? Which goes to 0. So you'd have infinitely small steps, no matter about this n squared, right? You'd have infinitely small steps. It would be like E0 would be here, and then E1 would be here, and then E2 would be here, and so on, right? So you would technically, this would literally be like a differential of an energy. It would be like a dE, and so the step, right? E2 minus E1, sort of, kind of, right? So you would have continuous energy spectrum. Whereas if you have like a really big width, I mean really big, with respect to the other constants, right? Because these are all really small as well. You've got, well, not pi squared, but h bar squared is super small, right? So a squared just needs to be a little bigger than that, and you've already got something that's not negligible, right, as a step. And then n squared, obviously, it's just gonna tell us that there's different states of energy. We're gonna check what this all means for our wave function. Now we can write out the wave function, psi n of x. We said that it was a sine kx, right? Well, what is k? K is just n pi, and then we can add x over a. That's what our k was. So this is our wave function, and it also depends on n, right? So what we've actually seen here is that we have different solutions depending on what n is. And also the energy depends on that as well. Well, what does that mean? Let's draw out the potential well again. So this is our 0 and our a. And this is v infinity, x. So let's see what happens if n is 1. Right? If n is 0, then we have psi n is equal to 0, so that's not an allowed solution. So we can see that, let's just get the a first. So we need the integral from 0 to a of a squared sine squared npx over a dx. We need that to be equal to 1. Well, let me just tell you this integral is equal to a over 2. Now you can do that yourself pretty easily. Just use that sine squared x is equal to 1 minus cos 2x over 2, I believe. Yep. Just use that. And then these are trivial to integrate. So from that, we get that a is equal to the square root of 2 over a. Yep, that's what a is equal to. So a is just always the same. Let's put that in here. I mean, it's always the same with respect to n, which is really convenient. It means that all of these have the same weight to them. Okay, that's pretty interesting. So we're gonna see what psi 1 is. Let me just change the order of these. Because I don't want this a to be bothering us. Oops. There we go. So let's see. Psi 1 of x is equal to, we've got the a over here, right? And then it's sine pi x over a. Well, what does this pi x over a mean? It means that when x is 0, it's got a node right here. We're going to be plotting, let's just make sure that we write it like that. Sine squared pi x over a. We're going to be plotting the square because we're interested in the probability, right? So this is psi of 0. Psi 1, sorry. Psi 1 of 0 is going to be 0 at 0 and 0 at a, right? Why is it going to be 0 at a? Because when we have a over here, we're going to have sine squared of pi. Sine of pi is 0. And that's the only node, right? Because it's going to go from 0 to pi. You could actually even simplify this and put in a substitution. We could say that x is ay. Would that work? Well, it's pretty much saying x over a is y, right? And then y would go from 0 to pi. Oh, yeah. Pi x over a is y, and then y would go from 0 to pi. What's nice about that is then we can obviously see everything, when the nodes are and everything. But yeah, this is pretty nice to see. So y goes from 0 to pi, which means that there's only 2 nodes, if we can call them like that. One is at 0 and one is at a. So that means that it looks like this. And we're going to say that we're going to be plotting all of these at the level of their energy. So we're going to have E1. We're going to say that E1 is the base energy, okay? Because what do we actually have? We have that En is equal to E1 times n squared, right? If you look at it, E1 is just without this. I mean, when n squared is 1, then it's trivial, right? So every energy, every consecutive energy is just E1 times n squared. I mean, you pick any energy, and it's just the first energy, the base energy, times the n squared, the how big the number is. So we're gonna be measuring in terms of E1, right? In terms of the base energy. So this is just 1 of E1. And then we go up to 4, right? We're gonna be going up to 4 and then up to 9 to find E2 of x squared. That's also gonna be 2 over a. So it's the same amplitude, sine squared. Now we got 2 pi x over a. So we're gonna have double the nodes, right? We're going up to here. It's gonna be 0 and 0, and 0 in a as well, because sine of 2 pi is 0. But we're also gonna have a 0 when x is equal to pi over 2. A over 2. Right, because we're gonna have just sine of pi, which was the one which had this as a 0. So we're gonna have a 0 in here as well. Now, if we had just psi 2 of x, it would look like this, but we've got this because we were only looking for the amplitude squared, right? We're looking for the probability. So what's interesting is that we've got the biggest probabilities here now. Whereas it was in the center of the well for this one, for the E1 energy. For the energy for E1, I'm just going to write it. I'm just going to write E1 for E1. Because n squared is 2 squared. That's why it's 4. If I wasn't clear on that. And now, so we took 2 steps here, so we're gonna try to take, oh well, that's not really discrete, is it? Let's say we take 3, technically it should be 9 by 2, which is 5.5. That's 3, 4, 5.5. I just wanna make sure that the spacing is right. That's good spacing, so that's 9 E1s. What's important is that the spacing keeps increasing, so it's not like it's constant spacing. It's because of the n squared, right? So this one's gonna be, well, time to move this stuff again. There we go. This one is going to be our psi 3 of x squared. That's also 2 over a sine squared. Now it's 3 pi x over a. And as you'll notice, this number inside, I mean n, it just makes it have another extra node. So we had 2 nodes for n equals 1. We had 3 nodes for n equals 2. And so we'll obviously have 4 nodes for n equals 3. We know there's a node here and a node here. Then where else is there a node? When x is equal to a over 3, right? That's when we'll have pi, sine pi. And when x is equal to 2a over 3 is when we'll have a sine of 2 pi. And then we'll have a sine of 3 pi at the end. So we're looking for a over 3. That should be around here. And then here. Say that's a over 3, and this is a over 2, obviously. Yep, So we've got something like that. Now, what's also interesting is for the integral to be, well, actually, I'm not going to claim that, so I'm not sure about it. I mean, all of these peaks are the same, you know? Yeah. The rise time is what makes it balanced out. So all of these peaks, let's mark them like this, I guess. This peak right here, with respect to this difference, is 2 over a, right? And it's the same for this peak and for this peak. What makes sure that the integral of that and the integral of that and the integral of that are equal is the rise time. Because, I mean, look at how long it takes him to get up. This integral is pretty big compared to this little integral, which is so fast. So that's why it stays balanced out, which is pretty interesting again. Like, especially if you looked at this guy here, it would, if you just continued this thing here instead, it would turn out to be the same. I guess that's a little bit confusing. I don't know why I said that. But yeah, so this is where you can see, excuse me. This is where you can see how the energies are spaced out. So yeah, there you go. That's the infinite well. Spaced out by energies. Now, obviously, so how did I plot this? I plotted it saying, let's call that plot P of n is equal to psi n squared plus En. That's how I plotted it, right? So the first one was plotted at E1 as the baseline, and then I plotted psi 1 squared, and so on, so on. But obviously, if you plotted just the psi n's, then there would be no reason to plot them like this. And if you plotted just the ENs, then they would just be a baseline, right? So if we wanted to plot ENs, for example, then we would get a really long line. I don't know how many I made here, but like if we had, let's say that there's 16 of them, and so you would have E4 over here, which is 16 E1s, right? Then you would count 7, 1, 2, 3, 4, 5, 6, 7, and then this is where E3 would be. Then you would count to 5, 1, 2, 3, 4. I don't know if I'm counting properly. 1, 2, 3, 4, 5, 6. Yep, need one more. E3 is here. And then 1, 2, 3, 4, 5. This is E2. And then 1, 2, 3. And this is where your E1 is. So look at that huge gap between these two guys. It's pretty much as big as this one, right? It's huge gap. And then the next one is going to be even bigger, right? And so you're just going to have like a baseline, obviously. And these are called energy spectrums. So this is why quantum mechanics is quantized, right? So you cannot have an energy that's here for the infinite well. You cannot have an energy that's here. You cannot have an energy that's here. Only these green energies are allowed. And they're absolutely quantized. If you wanted to get like an actual real number in a measurement, the best option you'd have, I mean probably not the best, but it's a pretty good option, would be to just fix this to that number and then find it in that n squared, because you cannot get anything except that number, right? If you wanted to get like you wanted to measure the number 1, you wanted to measure 1 joule, then you would set it up so that, I don't know, let's say this is equal to 1 joule, and you can never get anything different than that. That would be so cool, right? So you can pretty much be sure that you're getting discrete values, especially with this huge spacing. I mean, you can definitely be sure that you're getting discrete values, right? This is how quantum mechanics was predicted and proven and, you know, followed up on, because when they did it in the lab, they weren't getting anything over here. They were always, I mean, obviously you've got a little bit of lab error, so this green line is actually, it has like a width, right? This is like the error width. But that's because of the measurement, not because of the process. So look at these huge areas that you're never gonna get. If you have a theory that predicts this, it's so beautiful. Right, well, that's the infinite potential. Well, honestly, other than this mistake at the beginning, I'm pretty happy with how I taught this. I'll see you guys on the next one. I might not even redo this one. Bye-bye.